Welcome to our audience. I have top of the hour, so we are going to get things started and keep us on time. Welcome to today's webinar, Drilling for Thermal Projects, and thank you for taking the time to join us today. My name is Sue Bruning, and I'm the Marketing Director here at Cascade and your moderator for today's broadcast. In today's session, our presenters, Stefan Gripka and Rob Dankert, will discuss the critical role your drilling strategy plays in the overall performance of a thermal remediation system. They'll share valuable lessons through case study. And before turning the floor over to our subject matter experts, I have a few logistics to cover. All attendees are in listen-only mode, so that means that your lines are muted. Anytime during the presentation, you can type a question or a comment into the chat box on the right-hand side of your screen. At the end of the presentation, we'll address all of those coming through the chat box. And during that time, you can also click on the hand icon, which will allow me to unmute your line. The broadcast is being recorded and will be posted on Cascade's website shortly for viewing. And that's it with logistics. So please join me in welcoming Stefan and Rob. Stefan holds a master's degree in environmental engineering, and his thermal career spans nearly 15 years. Stefan recently joined the Cascade family with the acquisition of TerraTherm in 2015. He's responsible for the subsurface designs, including the numerical steam and TCH modeling conducted in the early design phase. Stefan leads TerraTherm's data management efforts and develops tools and systems allowing real-time client access to performance data during operation of our thermal projects. He also serves as the technical director and manages TerraTherm's technology team. Joining Stefan today is Rob Dankert. Rob has served as Northeast Regional Business Development Manager for Cascade Drilling since 2010. And prior to that, Rob spent 10 years in the environmental consulting field, specializing in subsurface contaminant investigation and remediation system design and construction. Rob holds a BS in environmental science and geology and is a licensed professional geologist in the state of New Hampshire. So without further ado, I'll turn it over to Stefan and Rob. Take it away, guys.
Thank you, Sue, for the introductions. So, starting out, first of all, welcome everybody and thank you for joining today. To start off this presentation, I would like to refresh everybody's memories on what thermal technologies are out there and what we offer. The first one, basically we are looking at thermal conductive heating, we're looking at electrical resistant heating, and we're looking at steam enhanced extraction. Starting out with the thermal conductive heating technology, we are basically looking at technology where heating is governed by the thermal conductivity of the subsurface. And typically the thermal conductivity only varies slightly between the different geologies we normally are facing at the thermal site. So we are looking at a variation in the order of 3 to 5 times between, sand. We have clay, gravel, and silts at our typical sites. When utilizing the TCH technology, we install a heater in a small heater can, and we'll get more into the well construction later on. Next technology in the toolbox is the electrical resistant heating technology. When utilizing the ERH technology, the heating is governed by the electrical conductivity of the subsurface. The variation in the electrical conductivity is quite a bit more for the typical geologies, and we're looking at a variation in the order of up to 200 between the most common geologies. And therefore, it's a little more important when we utilize the ERH technology to understand fully what kind of geology and what kind of electrical conductivity or resistance we are dealing with in the subsurface. Last, we have the steam enhanced extraction technology, where we are injecting steam to deliver the energy into the subsurface. And obviously, the permeability of the soil is important when we use that technology. And as you all know, the hydraulic conductivity can vary quite a bit between the different geologies. So typically we're looking at variations in the order of several decades. So for the steam enhanced extraction technology, it's even more important that we fully understand the subsurface. So that was the subsurface portion. So we're looking at, what else is, what other supporting elements are in play when we look at a thermal in situ treatment system. The well field is connected to a treatment system, above grade treatment system that basically treats the vapors and liquids extracted from the subsurface. The treatment system can either be based on a GAC-based system, a GAC regen system, or maybe a thermal oxidizer if the mass is high. The energy typically comes from the electrical grid, especially for ERH and thermal conductive heating. When we are utilizing the steam enhanced extraction system, the boiler typically runs on natural gas or diesel if no natural gas is available at the site. The next couple of slides will just briefly outline what kind of wells we are dealing with at thermal sites. The first one is the thermal conductive heating heater boring. The thermal conductive heater element is installed in a 3-inch, typically a 3-inch carbon steel can. The annular space around the can is backfilled with grout. Typically, sand can also be used, but typically we use grout because when we work on thermal sites, the mass are typically pretty high as well. That's where the technology is best. And we definitely don't want any migration of nabble along the borings. And for the thermal conductive heating technology, we have an option to basically fully plug the annular space, and that's what we do when we can. Boring diameters are typically 4 to 7 inch, depending on the state regulations and the setup. And well spacings are typically in the order of 12 to 17 feet. Sometimes we do extract from co-located vapor extraction screens located right next to the heaters, but most often it's actually from separate extraction wells drilled and installed between the heaters. The next slide here basically shows a well field. This is one of the bigger well fields, a thermal conductive heating well field, but what you see here is the orange wells are the extraction wells, and in between you have the heater borings. The manifold piping, of course, are connected, connects the well field to the treatment system. Moving on to the next technology, the ERH technology. Here is a picture or a figure of a typical ERH boring. In this case, we are showing two electrode intervals, the upper electrodes, which also serves as an extraction point, and the lower electrode, which is basically a copper plate that is installed in a graphite or steel shot annular space material. So the ERH wells are designed to have a big surface area such that the power can get in contact with the surrounding soils, and that's exactly why we have the graphite or steel shot surrounding the electrodes. Boring diameters are typically quite a bit more than for the TCH wells, in the order of 10 to 12 inch, and the well spacing is in the order of 14 to 18 feet in the typical application. This is a picture of a ERH well field, and you may realize that it's not very different from the TCH well field. We still have cables going to the ERH electrodes, and we still have manifold piping to connect the extraction wells with the treatment system. The last technology, the steam enhanced extraction technology, relies on us being able to inject steam into the subsurface. Typically, the steam are injected at very specific injection intervals that we model to fit the site. If a site is steep, we need several injection intervals as well. And when that's the case, we try to install the injection screens in separate boreholes, simply because we don't want the different injection screens to short circuit in the same borehole. The boring diameters, when utilizing the steam enhanced extraction technology, the boring diameter is typically between 4 to 6 inch, and the screen, the injection screen itself, is typically in the order of 2 to 4 inch for the steam injection screens. When it comes to the weld spacing, the weld spacing is a lot higher, can be a lot higher when utilizing steam enhanced extraction technologies. We typically start at a weld spacing of 20 feet, but we have been as high as 60 feet and actually even up around 100 feet at certain sites. This slide shows, an example of a steam-enhanced extraction well field, and the orange wells in this case are the steam injection screens with a little orange steam regulator on each of them. And in between, we have multi-phase extraction wells that are connected to the manifold piping. And then, other than the heating wells, we also have extraction wells. So for the ERH and TCH technologies, we sometimes, as I mentioned before, extract directly from the borings, but more typical, at least for the thermal conductive heating technology and for the steam enhanced extraction technology, we are extracting vapors and liquids in between the heater borings. To the very left, we have a typical multi-phase extraction well, typically constructed out of a 4-inch screen with a pump at the bottom to extract liquids, and then we are applying a vacuum to the entire well to extract vapors. And MPE wells, we typically install in an 8-inch borehole. When it comes to the vapor extraction wells, they are basically the same as a multi-phase extraction well, except that they are smaller in diameter. Typically, we select 2-inch screens and risers, but otherwise it's the same, just without the pump. And last, we have temperature monitoring points at all our thermal sites. Those are installed in a 1.5-inch carbon steel pipe. And around the pipe, we put high temperature grout such that there's no temperature smearing up along the well, and such that there's a good connection to the surrounding subsurface. We also have horizontal wells and pressure monitoring points, but we'll not talk much more about that in this webinar. But it's basically the same concept with installing them when needed and required at the site. And now I will hand over the time to Rob Dankert, who will basically talk a little bit about the different drilling technologies or method we are using.
Good afternoon, everybody. Rob Dankert here. I am your drilling host, at least for this webinar. We are working on, here we go. A little technical difficulty there, advancing the slides, but we're in good shape now. So basically, four methods of drilling we're going to talk about here that will set a baseline for our case studies that we'll talk about later. Most of these methods are pretty common with you folks, I'm sure. We've got DPT up here that we'll touch on briefly, air rotary sonic, also known as rotosonic drilling, and then another option is vibratory hammer drilling method that we used at one site in New Jersey a few years ago. So direct push, again, I'm sure most of you folks are familiar with this process. It's a flush threaded casing. It's pushed with a static hammer, or a static weight or percussion hammer through the subsurface. It's usually advanced, at least for thermal purposes, in support of TMP installation. So we're normally advancing a 3.5-inch diameter casing of 4-inch through the subsurface. There's an expendable point that's at the bottom of the casing that forces the formation material into the formation, or the displaced material into the formation. And again, it's flush threaded casing, so we're setting whatever component of the thermal tooling that we're setting is installed inside of a temporarily cased hole. It's very economical and versatile, as everybody knows. Geophobes are relatively cheap compared to other methods. Unfortunately, they're generally, some people may disagree, but they're most often used in shallow, unconsolidated geologies. And depending on the rig, they can be susceptible to shallow refusal. Here's a couple photos of some DPT rigs. We've got the Geoprobe 8040 on the left and Geoprobe 78 series on the right. These are two of the rigs that we would typically use when we're asked to install thermal components. They are beefier rigs. They can both push 3.5 or 4 inch diameter tooling, which is the size that we would need. Hollow stem auger, again, I'm sure you folks are typically familiar with this. You've got auger bits that claw through the formation. Formation material is brought to the surface via the auger flights. I usually have someone at the surface that's shoveling that material into a 55-gallon container. And the auger flights are hollow, so it's that hollowness of the augers that allow us to install subsurface thermal components. The diameter and depths are dependent on torque as well as geology. Usually for ERH sites, we're typically advancing 12-inch diameter OD augers, which are pretty large, and they tend to be a little bit depth limited. So I always get a little leery when folks ask for 12-inch diameter augers over 30, 35 feet, depending on geology, of course. Here's some standard auger rigs. They come truck-mounted and track-mounted. Direct air rotary is another method that we typically use, obviously for rock remediation sites, thermal sites. Tricone hammer bit is advanced through the bedrock, and cuttings are brought to the surface via an onboard compressor or standby compressor. The compressed air brings the formation material to the surface, where it's sent through a cyclone or discharged directly into a roll-off container, 55-gallon drum. The method of stabilizing the borehole is inherent to the stability of the geology, right? So we're not typically using air hammer to drill overburden material. It's usually only for bedrock, with the exception of some other air rotary methods that are used out west. One of those methods would be air rotary casing hammer, although ODEX is another method, a casing advanced system that's occasionally used here in the Northeast. Need consolidated material to keep the borehole open. That's sort of implied with the bedrock nature of the drilling. It does produce formation water in protected zones, so if you're drilling in rock and along the coastal plains, you'll likely get a fair amount of water generation. Here's a standard sonic rig. This is another method that we typically use. This one tends to be more common for us. This is a Bort Longyear model mini-sonic rig. The operation of the rig is completely different than the other rigs I've mentioned. It's primarily based upon an oscillation module that's present in the sonic head. In the image on the right, you can see the head at the top of the mast. The oscillation module has two cams that rotate at variable frequencies. And those frequencies can be adjusted to create resonance along the drill string. That resonance is typically what allows the sonic tooling to advance through boulders and cobbles and material that typically causes refusal for augers or probe rigs or other conventional methods. It's a two-step process. So you've got a core barrel that's advanced in 5 or 10 foot long runs, and then it's overridden by a temporary casing. The core barrel then comes out of the surface, or is pulled out of the surface, and is typically extruded into a polyethylene liner. And then the process is repeated. So you've got a core case process. Here's a photo of the core barrel that's come out of the surface with a polyethylene liner wrapped over the barrel. The sample is then extruded from the core barrel directly into the liner, typically for characterization purposes. Here's a couple photos of some 5 foot long cores. We've got some urban fill at the top, gravelly material on the bottom. Here's some basal till up in the top left image. We've got some fist-sized cobbles in the top right. Those were captured with a 8-inch diameter core barrel. In that instance, the concrete in the lower left, that's evidence that we can, a sonic rig can typically advance through that type of material, as well as steel rails, which are shown on the lower right. Those rails were drilled through during the Central Artery project in Boston, Massachusetts. It was probably 12, 15 years ago. also known as the Big Dig. Vibratory pile driver. So this is a relatively new method for us, and we're really pretty excited about it. We used it a few years ago in New Jersey. It's also based upon an oscillation module that creates high-frequency vibes. That module, in this case, or in most cases, is mounted to the end of a typical yellow iron excavator. This allows us to advance tooling, heater cans directly into the subsurface. And this method is typically used for driving sheet pile walls or piles directly into the subsurface. Obviously, there's no IDW generation because we're advancing that heater can directly into the subsurface. It is direct drive, so there's no need to stabilize the borehole, and it's really economical and versatile in shallow, unconsolidated geology. Right, so the geology has to be amenable for us to use this. Otherwise, we can snap the heater hands pretty easily. You want to take this one?
Yes. Thank you, Rob. And I'll continue. We'll continue by presenting a case study from the Solvents Recovery Service of New England Superfund site, where basically preventing NAPL migration during drilling was a big topic, simply because the site characterization basically clearly showed that there was a lot of NAPL present at the site. And obviously, the drilling, with the drilling and the well installation, we didn't want to mobilize this NAPL into the underlying bedrock. At the site, we basically went with a 14-foot heater spacing. And what was kind of unique here was that the geology at the site had a sand layer at the top, underlain by a till layer. And then below that, there was a weathered rock, and roughly a few feet into the weathered rock, the more competent rock was located. In general, prior to basically the thermal construction feasibility study at the site, that included basically constructing or doing a lot of pushes using a geoprobe rig at a 20-foot grid, revealed that the bedrock was probably located at a certain depth. And what we found during well installation using the sonic rig later on is that initial bedrock was actually the top of weathered bedrock. The sonic rig, we ended up tying the heaters on average 3 feet deeper into the bedrock that initially envisioned. So between the design and the actual startup, the volume actually increased by more than 20%. So in terms of the well installation, I will hand it over to the next slide, actually, if you can advance it. There you go, yes. So we were looking at installing a lot of wells at this site. We had a total of 607 heater wells and a total of 550 co-located vapor extraction wells. Together with the temperature monitoring points and the pressure monitoring points, we were looking at more than 1,300 borings to be installed at this site. And obviously, it was super important that we didn't mobilize any NAPL into the bedrock. And the technology and the method we used there will be further described by you, Rob.
Yeah, thanks, Stefan. Folks, sorry for the little bit of a delay on the slideshow here. So Stefan mentioned sonic drilling was really the method that we chose on site for a number of reasons. This highly dramatic photo here of the helper standing in front of the sonic rig is one that I kind of like. Background is the SRS site. Here's a general photo of the site, and Stefan had mentioned one of the primary concerns was limiting the migration of DNAPL as we were advancing. So here's a diagram of some of the well installation technique that we used. So 6-inch diameter casing was advanced through the subsurface and through DNAPL zones, as well as isolation casing to isolate some of those DNAPL zones in both overburden and in bedrock. So in this here, where you can see that we're advancing several feet into bedrock and limiting that migration of DNAPL into rock. The next slide here shows the construction of that heater can and other thermal components. So as I mentioned earlier, the heater can was installed inside of a temporarily cased boring. One of the advantages was that as we vibrated the sonic casing out of the subsurface, we termigrouted as well, and that vibration caused the termigrout to stitch itself into the overburden and bedrock formation, ensuring that there wasn't any bridging as well as a continuous seal. Here's another image of the casing being pulled out of the subsurface and the grouting of the annular space. One of the other concerns was urban fill on site. We had known that there were prior buildings on site, and they had been raised over time, and due to other excavations on site, we had seen some concrete fill that was present up to 8 inches thick. Sonic was chosen because we knew that it would be able to advance through that urban fill and minimize any delays in production rate. One of the other advantages was that we could collect continuous cores of the subsurface, so we could really verify where the top of rock was, as well as look for any presence of DNAPL in the sample core. So as I mentioned earlier, we could get continuous cores of the rock itself, or of the overburden and the rock. Most of the sampling that we did was pretty basic field sampling for DNAPL, using the jar shake method and also having a PID of site. If we did find a presence or the potential presence of DNAPL in the soil core, we were able to collect a groundwater sample from the base of the sonic casing. And it's not the cleanest method, but because we were able to drill dry on site, I forgot to mention that earlier, that we didn't use any water or drilling fluids when we were sonically drilling, and that was a key component of ensuring that we didn't have any, or we didn't cause any migration of DNAPL during the drilling process. So yeah, so these photos here show us just installing some polyethylene tubing to the base of the cased hole and pumping on that formation water via peristaltic pump to verify whether there was in fact DNAPL, or at least recoverable DNAPL. Another advantage was that we were able to directly discharge the IDW into 5-gallon containers or a skid steer bucket. In this photo, you can see that in situations where we didn't need to characterize the borehole or the soil, we could discharge that core barrel or the contents into the 5-gallon bucket. Certainly better containment than an auger method, where, as most of you folks know, those cuttings may be brought to the surface, and you've got a helper out there that's hand shoveling that material into 5-gallon containers. Here's a plug for Sue Bruning and sustainability. Because we were able to verify where the top of rock was, we could minimize any excess steel or waste steel. So we fabricated all of the heater cans on site and installed them using this lull in the Minisonic loader shown here in this photo. Here's a photo of the actually after construction, right, Stefan? Do you want to take it?
Yes, that is actually a picture of the well field prior to installing all the manifold piping. All right, so the next case study we brought today is basically the Teterboro, New Jersey site, where, you know, the challenge was this was a very big site. It was a 3.2 acre site, And with the wells that we needed for the thermal remedy, this is another thermal conductive heating project. We actually ended up having to install nearly basically more than 1,000 borings, and most of them were heaters. 907 of them were heaters, but we also had some multi-phase extraction wells and some pressure monitoring wells and TMP strings. At this particular site, we were dealing with a fill layer underlain by a 8 feet sand layer, and below that we had silt and clay. So to the bottom of the site at certain areas was 40 feet below grade. And since, as discussed previously, the TCH heater borings doesn't require annular space, and you know, it was an obvious choice for this site to try to direct or vibrate the wells down, simply to cut down on IDW and bring up the well production. So Rob, I know you have something, some details about that process.
Sure. So for Teterboro, TerraTherm subcontracted DA Collins out of New York to use that vibratory hammer that I mentioned earlier to advance some of the heater borings. This photo here is of the vibratory hammer that we used, also installing pile drivers for a sheet pile wall. Here's a photo of the oscillator, the vibratory hammer, with a sidearm grip that was advancing these our 3-inch diameter heater cans directly into the subsurface. So most of the heater cans were installed using the vibratory hammer, and it was unique for the TCH heaters. We didn't use them for any of the other subsurface components. And it was certainly much faster production rate than any other method we could have used. Our production rate was roughly 500 feet per day. And obviously there was minimal IDW generation because there was these were able to be driven directly into the subsurface. We did have some issues on site. We had some breaks at the welded joints. The breaks occurred obviously because of the vibration. The vibration snapped a couple of those welds, and we did have some overheating of the hammer, which caused some delays on site. There were subsurface footings on site that caused refusal, but if we did hit refusal, we offset roughly 1 to 2 feet adjacent to that original borehole and tried again. And if we did hit it a second time, then we reserved that hole to be completed with a sonic rig, which later came on site to basically do mop up of any remaining holes. We also fabricated a sleeve to enclose the weld joint on each of the heater cans. This helped reduce the vibration that caused some of the breaks in the can. So we obviously had substantial cost savings with this method. 90% of the heaters were installed with this vibratory hammer, and the remaining 10%, or approximately 10% of the cans were installed using sonic. The final cost of the heater can installation was less than half of what it had been if we had used sonic drilling for all of the heater can installations, and the net result was roughly $500,000 for the client. Stefan, you want to talk about hot soil sampling?
Absolutely. So the last topic of today's webinar is basically hot soil sampling, and obviously this is a topic that comes up on a lot of our sites because that's the way we document that the thermal remedy is complete and that we are ready to turn off the system and document that we have reached the goals. When it comes to hot soil sampling, it's of course super important that none of the VOCs that may still be present in the soil samples are lost during the sample process. So typically we prefer to collect intact cores to limit any vaporization of contaminants during the sampling process. The samples are typically collected using a Corbel type sampler, and we typically collect the samples in stainless steel sleeves or Teflon sleeves. The length and the diameter of the sample tools varies from drill rig to drill rig, but we try to limit the length to 5 feet, simply to make sure that the quality of the samples are high enough, and we don't mix it all together. In terms of sample collection, you know, it's very similar to what you would do on a cold site. The core bell is advanced to the desired depth. The samples are collected, and the sample is brought to the surface. One thing that we see a lot is that it's hard to get full recovery, and typically that's due to the fact that no matter what thermal technology we use, we will evaporate some of the pore water and decrease the saturation, and other, you know, in some instances the soil will also be harder after we basically evaporate that water. But in general, the standard drilling equipment are utilized, and the sample process, or the soil, bringing the soil to the surface, is relatively straightforward, just with a bunch of hot work procedures, of course. Once the sample are brought to the surface, now the fun begins. First step is to cap the sample, of course, and make sure that we don't evaporate the chemicals as discussed before. We then cool down the sample, typically in an ice bath like shown in this picture. We are aiming to cool the sample down to at least 50 degrees Fahrenheit or 10 degrees Celsius, since that's close to ambient temperatures in most regions. And at that point, we are ready to collect the samples. Sometimes we basically just ship the samples in the sleeves directly to the laboratory. Sometimes we take the soil out of the sleeves and put it in bags or jars. And at some sites, commercial systems like the Encore system or sample system are used to collect the actual sample. It's typically a big concern for the client and the consultant if this hot soil sampling procedure, when properly followed, actually will provide a good indication of what the actual soil concentrations are at ambient temperatures as well. So this chart basically shows a sample result from a site in Denmark that we completed a few years ago. The client, the region of Copenhagen, was very concerned that the hot soil sampling procedures basically would provide the right indication of where we were at. So they asked us to come back 2 years later to verify the results that was obtained during the hot soil sampling effort. On this chart, we have the soil concentration on the x-axis, and we have the depth in meters below grade on the y-axis. All the red dots are basically the pre-treatment concentrations. You'll see that we collected a total of 38 samples, and the maximum concentration detected at this site was 360 milligram per kilogram, indicating that NAPL was actually present prior to the thermal remedy. The average concentrations was 41.3 milligram per kilogram. After roughly 7 months of operation, we decided it was time to document that we have reached the goal. So we initiated a post-treatment sampling event, collecting 67 samples, and found a maximum concentration of 0.057 milligram per kilogram. So definitely below the side goal of reaching a concentration of 1 milligram per kilogram. The removal efficiency was calculated to be between 99.9 and 100%, and that's actually pretty typical for a well implemented thermal remedy. We then let the site cool down and came back 22 months later to perform a second post-treatment sampling event. During that event, 5 borings was drilled at the site, and 17 samples were collected. And basically all of the samples were non-detect with a detection limit of 0.01 milligram per kilogram. And that's all the green dots you see on this chart. So that basically confirms that the hot soil sampling technique was providing a good indication of the efficiency of the remedy. And actually it also indicated that we have had some kind of polishing in between, which is very typical at thermal sites, that in the cool down period some polishing takes place. So to wrap up this webinar, first of all, it's important that there's a good dialogue between the thermal vendor and the drilling contractor, and of course the client and the client consultants about how to install the well field. The drilling cost of a thermal project is typically between 10 and 20% of the total remedy cost. So it's important that it's efficiently performed. Other than that, when it comes to select the right drilling technology for a given site, it definitely depends on the heating technology selected for the site, but geology, the boring depth, the boring diameter, and the location of the water table definitely plays into the drilling technology selection. And also, as Rob indicated, if we know there's a lot of refusal present in the upper portion of the site, we tend to lean towards selecting sonic, because it's a lot easier to get through concrete slabs and so on when using the sonic technology. For thermoconductive heating and steam enhanced extraction projects, we typically use sonic. First of all, because we see a higher production rate, and second, because the technology is less likely to be stopped by refusal. In general, we also create less IDW using the sonic technology, and also actually from a practical standpoint, bridging during when we set the sandpack or when the grout plug is put in the wells is less likely to happen due to the sonic vibrations. And then in general, we see a trend, we offer all three technologies, and we see a trend that for the deeper side, TCH and steam enhanced extractions are typically the most cost-effective technologies. So at least the way we implement projects, we see a trend that those technologies typically go deeper, and when we go deep, sonic is the best and cheapest way to construct the wells. For ERH, we often use hollow stem auger. One of the reasons is, of course, that the wells are bigger, so larger diameter borings is cheaper with augers. And as I mentioned before, since the ERH sites generally, are more shallow, it makes more sense to use the hollow stem auger technology. So Sue, that completes the presentation.
Great, thank you, Stefan, and thanks to Rob. We do have a couple questions that came in during the presentation. We'll start with those. If anyone in our audience has a question at this time, feel free to go ahead and type that in your chat box, or you can click on the hand icon by your name, and I'll be able to unmute your line. So the first question, Stefan, is for you, and the question is, at what soil resistivity would you consider TCH over ERH?
That is absolutely dependent on the site setting, of course, but we have a rule of thumb saying that 500 ohm meters is pretty much a good number for when we start to have to do separate design mitigation for our ERH system to create a effective ERH well field. So, of course, we have implemented ERH projects at resistivities all the way up to 2,000, 3,000, 4,000 ohm meters, but it does require, sometimes a tighter well spacing or electrode spacing. It does require, we're basically adding more amps to the subsurface, so it beefs up the cables and it adds cost to the project. But you know, a good rule of thumb that we use internally at least is 500 ohm meters.
Good. The next question is directed to Rob, and it's with respect to sonic cores. I've heard that they can be pretty hot. Do elevated temperatures typically get very far into the core as opposed to heating just the outer skin?
So I will take Stefan's pass, I guess, and say that it is formation dependent. What I find is it depends on how hot the core barrel is itself. Typically, the minimal core barrel size is 4 3/4 inch diameter, and obviously, if you're really concerned about temperatures, I would use one of those digital thermometers and bring it on site. And if you're collecting, say, a VOC or 8260 analysis or sample, I would use one of those on-core samples and collect it as close as you can to the center of the sample. So I certainly don't know. I mean, I can't say with certainty how far into the sample or how far into the core temperature would be affected. Again, I think it's temperature dependent, but you can verify that by bringing one of those digital thermometers out there and see what sort of impacts there are.
Thanks, Rob.
Sure.
The next question, I'm not sure who this is directed to exactly, so I'll throw it out to the both of you. The request is to comment on decommissioning or abandonment of boreholes.
That's probably you.
Yes, I can take a pass on that. So I think what we have seen on our thermal sign is that it varies from site to site what is required for thermal conductive heating site, and actually for your site as well. We basically try to get permission to grout up the wells using at that point it doesn't even have to be a high temperature grout, but that's by far the cheapest way of decommissioning the well field. So grouting up the wells, sometimes high pressure grouting them, and then cut the wells at grade. If that is not, if we due to regulator requirements are not allowed to do so, the only thing we pretty much have left is to overdrill all of the wells, and as you may imagine, that's pretty costly, and actually typically will cost close to as much as it initially cost to install the well field back in the day. So, Rob, I'm sure you can probably verify the numbers, but that's what we typically see.
Yes, I agree.
All right, thank you. That's all the questions that we've received. We've got one more coming in, and we've got time to field that. So, do you see differing ranges of ROI for heating various bedrock lithologies?
To be honest, no. So we pretty much every time we complete or conduct a thermal project in the bedrock, we tend to lean toward the thermal conductive heating technology. Simply because to utilize ERH in bedrock, we need to have some resistivity that is down in the range that we can handle, and to have a low enough resistivity of the bedrock, it also requires it to be pretty permeable, such that we, basically it's the porosity and the saturation of the bedrock that lowers the resistivity. So when we implement bedrock sites, it's typically the thermoconductive heating technology we use, and for those, the bedrock, the variability of the thermal conduction is within the range that I mentioned before, so very low range between 3 to 5, and the heater spacing is basically kept to spacing just around, I would say, 13 to 16 feet in general. So not a very high variability.
Okay, and one more question came in. What is the average cost per cubic yard for ERH and TCH?
Yeah, we get that question a lot. I can tell you that much. So that it's very difficult to generalize that way because we basically customize the thermal solution to the site, right? And you know it all depends on, are we in the Veda zone? Are we in bedrock? Are we in under saturated conditions where we need to pump a lot of water to maintain hydraulic control? So, you know, I can, you know, one of the cheapest projects we've done, we had a unit treatment cost of $71 per cubic yard using the thermal conductive heating technology. And that was basically at a site with 8 different source zones. So we were able to, it was a fairly big site, and of course, as the site shrinks in size, the unit treatment cost basically grows, and that's because we always need to mobilize a treatment system. We need to submit a design and so on. So generally, what we're seeing in the market, just also comparing to what sites do we win with the different technologies. I really can't say what a typical cost is, but the most expensive sites that I can recall, we were looking at a unit treatment cost up around $1,200 per cubic yards, and that was a pilot, and the small volume basically drove up the cost.
Okay, thanks, Stefan, and thanks, Rob. That's all the questions we have for today. And I'd like to thank our audience as well for taking the time out of your busy schedules to attend today's webinar. I hope you've enjoyed the session and have really been able to get some good information from it. Please be sure to check out future webinars and sign up for our webinar invite on Cascade's website at cascade-env.com. And as you log off, you will receive a request for a brief survey. I thank you in advance for taking a few minutes to provide feedback on our session today. We really do read every survey in an effort of continuous improvement. So with that, I will sign off. Thank you, Stefan. Thank you, Rob, and have a great day, everybody.
Thanks, everybody, for joining.